Okay, well, we're, I think, done with acids and bases and nucleophiles. What we need to talk about now is stereochemistry. And we don't want to spend too much time on it because you guys should already be very good at stereochemistry. If you struggle to identify R versus S, you better figure that out. Not that I'm going to test it, but that you're going to be embarrassed someday. If you struggle to identify enantiomers and diastereomers, you also better figure that out. Let's see. I feel like this is Alma Chapter 5. Is there any among you that is not sufficiently able to distinguish between enantiomers and diastereomers? If so, I would say that such a one must prepare, and he should prepare quickly, for the day cometh when, yeah, anyway.
I like this chapter.
All right, so I want to just mention a few things that you'll, in terms of terminology, that you will hear. Of course, the term stereoisomers should be familiar to you. That's same connectivity but different arrangement of atoms in space. Okay, so that includes cis and trans alkenes. There can be stereoisomers, even includes conformational isomers, like the two different gauche butanes or the gauche and anti-butanes. Constitutional isomers have different connectivity, so that's a different thing. And almost nobody uses constitutional isomers anymore. It's kind of like a mouthful. What people do use is regioisomers, which have almost the same connectivity, but they differ in the location of a couple of groups. At least one, or anyway. A regioisomer would be like ortho versus meta substitution on a aromatic ring. So stereoisomers include enantiomers and diastereomers, and that's actually the only two kinds of stereoisomers we have. But included among some, included in either of these terms, we have to include conformational isomers. And whether or not we say things are conformational isomers, well, whether or not we pay a lot of attention to conformational isomers is going to depend on the rate of interconversion. So there's a whole class of chiral molecules that are called Atrope Isomers, where they can interconvert by rotation about a single bond, but the single bond rotation is very slow. So the two different conformational isomers can actually be separated and used differently. And we'll talk about some of these. Some terms. So overall, if two stereoisomers are not enantiomers, they have to be diastereomers. So if you have a hard time remembering that, you need to go look up the VeggieTales Silly Songs with Larry, where, and I think the song is called It's Not a Monkey, It's an Ape. And in that, Larry the cucumber assures Bob the tomato that Larry has like a single tooth. He looks kind of psycho. I need to make there we go, a little more goofy. Assures Bob the tomato that if it doesn't have a tail, it's not a monkey, even if it's got a monkey kind of shape. If it doesn't have a tail, it's not a monkey. If it doesn't have a tail, it's not a monkey. It's an ape. And Bob, of course, tries to point out the logical inadequacies of that characterization. pointing out that lots of things don't have a tail. A cow has a tail, then it's a monkey. Anyway, in the same way, if it's not an enantiomer, it's a diastereomer, even if it has an enantiomer kind of shape. I used to play that in 351 and 352. Some of you have probably seen it before, so I don't want to do it again. But go look it up after class. It's kind of fun, and it'll get stuck in your head. All right. So, and enantiomers, of course, are non-superimposable mirror images. That's easy. Though there's some actual technical symmetry terms which come up later in the chapter, which we'll talk about. I don't really understand them that well. But chirality and stereoisomerism is a big part of point groups and symmetry operations, and so you can look at things that way. Some terms that can generate confusion that you will hear in OChem talks include optically active. Optically active means a compound that rotates plane polarized light. And optically active compounds are chiral. They have to be. But not all chiral compounds rotate plane polarized light by a sufficient amount to measure at all wavelengths. So you could have you could envision experiments where you try to measure the optical rotation of a chiral compound and it's too small to measure, or you have a racemic mixture of two enantiomers. They're both chiral, but still there's no optical rotation. So we don't use anymore the term optically active to mean that it's chiral. We just use that term to mean it rotates plane polarized light. We're going to talk about why that particular experiment distinguishes between enantiomers. Go ahead.
Racemic mixtures are not optically active, right?
That's right. They're not optically active, even though every molecule in that mixture is chiral.
Some molecules rotate light one way, others rotate it the other.
Right, and it cancels out. The effect cancels out. There are some other terms we don't want to use at all. These include chiral center or chiral carbon. You will still hear this from respected chemists. You'll hear it more from biochemists than you will from chemists. But as organic chemists, we don't really like it because the whole molecule is chiral. So people have typically referred to a chiral center as any carbon that's not attached to four different things. Any carbon that's attached to four different things is a chiral center. Well, we have lots of chiral molecules that don't have carbons attached to four different things. So that's kind of ambiguous. And again, in a chiral molecule, every point in that molecule, atom or not, is chiral. It's a chiral environment. So it's not like chirality is associated with a single center. Another term that has fallen out of favor is asymmetric carbon. And I think that has generally been used interchangeably with chiral center, and its use is discouraged. Instead, there are two terms that have replaced a lot of this, and one is Stereogenic Center. That is a center that generates stereochemistry. And this, or Stereo Center for short. And the easy way to think about a stereo center is interchange of any two groups. Interchange of two groups gives you a stereoisomer. So this encompasses the classic sort of thing you would have thought of with chiral carbons or chiral centers. That is, if we interchange these two groups, we have another enantiomer, right? But it also is a little bit broader. There are molecules, actually, let me do something like a ruthenium complex because I don't know anything at all about metals, but this is an example of a stereogenic center that is not attached to 4 different things. It is attached to lots more different things. So this is a ruthenium, looks like octahedral complex. I'm making stuff up at this time, so at this point, so those of you that are in 514, you can tell me I'm crazy. It turns out that even though we've got 3 of one and 3 of another, if we swap 2 of them, we've got a stereoisomer. And this can be difficult to see if you don't make a model. And so you may have to convince yourself that this is true. Okay? Different stereoisomers. Now that's an example the book gives. I'm having a hard time as I draw it figuring out, oh, those are different things. But yeah, go ahead.
Yeah, I'm in 514, we've done examples like that. The way you can easily tell those apart is that one has all the chlorines cis to each other and the other one has 2 trans.
Okay.
And also, you mentioned there are some molecules that don't have chiral centers, but they're still chiral.
Yeah.
In the past, we've learned about molecules with chiral centers that are not chiral. But
Right, absolutely. So you can, meso compounds, that's another reason why not to use it. Meso compounds have stereocenters, but are nonetheless achiral. And a fun one to, I occasionally have given this on a 351 exam just to play with people's minds. It depends on a very obscure rule for assigning stereochemistry, but we'll go ahead and talk about it. These 2 alcohols, the one on the right, except I got my left and right wrong the first time. It happens all the time. My brain has some chirality issues. The one on the left is achiral, and the one on the right is chiral. Okay? Now we can ask, that's fine. How many stereocenters do we have in each of these? Well, we'll number carbons. Carbon 1 has R stereochemistry. Carbon 2 has S stereochemistry. Over here, carbon 1 has R stereochemistry, and carbon 3, I'm sorry, I said carbon 2, also has R stereochemistry. What do we do for poor old carbon 2? Is it really attached to 2 of the same thing? Connectivity-wise, it looks like it, but it only counts as being the same if the stereochemical configuration is the same. So it turns out that because of that, these 2 groups are different from each other, and the R one gets priority. So we would say this middle carbon is R. However, in the structure to the right, you've got now 2 of the same thing, and so the carbon in the middle is not a stereocenter. So ironically, well, it's not, that's an improper use of the word irony, I suppose. In a way that seems counterintuitive, carbon 2 is a stereocenter in the achiral molecule, whereas carbon 2 is not a stereocenter in the chiral molecule. All right. Yes?
Sometimes I remember talking about how stereocenters cancel each other out, and so I guess I'm having a hard time with the one on the right. Sorry, this one, that one.
Left. You did it too!
I was talking about you looking at the screen and you're right.
Oh, okay.
I wasn't. I wish I could be that smart. So I feel like the R and S would cancel each other out, and then you'd be left with just an R, right? Or is that incorrect? I mean, if it's achiral, that's incorrect, so I'm curious how you think about it.
so there's no, can you say that again? Because I'm not sure I understand the
So
question.
normally I think about the
At this stereo center?
1 and 3
Yeah.
are identical but opposite, and so they cancel each other out, and so the one in the center takes precedent. But it's obviously achiral, so that's not exactly what it's
So I think it sounds like what you're saying is derived from a simpler but classic example of chiral versus achiral molecules. This, I think, we used in 351 to demonstrate that you can have stereocenters and still be not chiral, right? Because here the stereocenters are both R, whereas here one is R and the other is S. So in that specific example, you may have, knowing that this was achiral, used a mnemonic device. Well, if it's the RS 1,2-butane diol, then it's a meso compound, and I'm just imagining that the R and the S cancel each other out. That's a decent mnemonic device. Unfortunately, it only applies in that situation.
Gotcha.
Or it will apply for meso compounds, right? In general, meso compounds have stereocenters but are achiral. They have a plane of symmetry through the middle. So yes, the stereocenter on the left is going to be opposite to the one on the right. But the thing that makes it achiral is that it's not superimposable with its mirror image. Yeah. So, and all of this would break down, of course, if one of those OH groups was something other than, yeah.
That's why they wouldn't be.
They don't cancel each other out. Yeah. Yeah, exactly. So it'd be kind of weird. All right. And I'm going to erase those because I'm afraid that I drew them opposite where they should be. The one was not chiral and so on. Okay. So, Stereogenic Center. Some people have used the term stereogenic center even with alkenes. I think if you do that, you're going to confuse people. Of course, if you interchange two groups for this trans-2-butene, you're going to get cis-2-butene, which is a diastereomer. But so technically you could call that a stereocenter, but again, you're going to confuse people. Perhaps more appropriate is to say, hey, this is a stereogenic unit because interchanging two groups on either side will give you a stereoisomer. So other examples of stereogenic units include molecules that have no classically defined stereocenters but are nonetheless chiral. This kind of molecule is called an allene, and you may have encountered it before in 351. It's used as an example of sp hybridization, and also to give you a sense that the double bond on the left here has p orbitals that are orthogonal to the double bond on the right. We okay with that? You look at that and you can see that. Okay. So carbon 1 is in the plane, has its substituents in the plane of the page. Carbon 3 cannot. And so it'll have a substituent coming out at us and a substituent going back in the page. Now, you're going to have to bust out your three-dimensional visualization qualities because we're going to go through the looking glass. Oh, man. Why don't they... That's what they should have called this chapter, right? Through the looking glass. We're going to draw the mirror image of our compound, and we're going to convince ourselves that there's nothing you can do to interchange A with B. All right? remember, there's no rotation around double bonds, so those groups are locked into place. And I suppose if you grab either methyl group and then try to spin it around, that is, what if we put an axis here and tried to rotate and see, can't we get that to happen? Well, then the methyl group on carbon 3 would be in the back and the proton would be in the front. Okay, so do you believe me that those are two stereoisomers? They're non-superimposable mirror images. In fact, these are enantiomers. But there's no classically defined stereo center, so you could talk about this stereo as a stereogenic unit. Go ahead.
So these compounds are optically active then, even though they have no carbons connected to 4 units?
Yes, if you are chiral, you could be optically active. Now, whether or not something rotates plane polarized light to a significant extent will depend on physics and the structure. And so I don't know whether this has a measurable optical rotation at any wavelength, but it could. Yeah. So we will call this each of these molecules, B is chiral and A is chiral. They are enantiomers of each other, even though there is no stereo center. Instead, we have a stereogenic unit where interchange of two groups can generate stereoisomers. Now, you might want to know, how do we, nomenclature R and S, E and Z, we're not even going to talk about. You ought to be able to do that. Yes?
Is there a system for assigning R and S with these?
Yep, we're going right there. So this is an example of what's called helical chirality, where if you look, you can envision an axis, and if you look down one end of the axis, the two enantiomers appear differently. So having defined our axis, let's put at this time of the semester, our Sith eyes can be bloodshot because Halloween is approaching and we're tired. So let's draw a Newman projection looking down and show what we might see. So in the front, we'll have proton to our right and methyl group to our left. I think this problem I have with right and left, I think it's genetic because my grandpa, I think, has it too. Like, my grandma will make fun of him, laughing that when she says it's on the right side, she'll have to add, "Throw a rock, Dale, throw a rock." And he has to, okay, that's the right side. Anyway. So what you do to assign chirality of a helical chirality in this way is you look at the carbon in the front. It turns out it doesn't matter which one you look at. We can convince ourselves that that's the case. But you look at the carbon in the front, and you identify, just like with E and Z, the highest priority group. And in this case, it's the methyl group. And then you do the carbon in the back. What's the highest priority group? Okay, it's the methyl group. Then you ask yourself, if I draw a sort of circle from starting with the one methyl group in the front to the one in the back, what's the sense of that rotation? It is clockwise. And so the correct term for that, and I don't want to get it wrong, so I'm going to make sure we get it. Clockwise rotation, or in other words, we're rotating to the right. That's called P for plus. All right. And did we ever find out where R and S were from? I think it was, R and S were from Latin, E and Z were from German. Thankfully now we've got something from the good old language of English, plus and minus. So the other enantiomer would be M, and we can convince ourselves that that's the case by, and because looking down this axis, it's a right-handed rotation, we'll say this is a right-handed helix. It's called a helix because, of course, it's a rotation that propagates down an axis. If we do the same thing for the other enantiomer B, again, we'll see that going from the methyl in the front to the methyl in the back is counterclockwise or to the left, and for us that's going to be in the minus direction. I'm really sorry because I realize that in the math and physics world and with polar coordinates, counterclockwise is positive, but I didn't make up the rules. All right. Any questions about that? P versus M. Yeah.
Yeah, comment with that. With the polar coordinates that you always learn in math class, counterclockwise is positive, but if you look at the coordinates on your compass, clockwise will often be positive.
Yeah. So what I suppose that may be a deep-seated argument between right and left-handed people, and I don't know who controls the world. Probably the right-handed people, because left-handed folks figure very early when doing scissors in kindergarten that the world is not for them. So, all right. I actually have a lefty son, which is kind of fun. I'm trying to. There was a funny story, but now I can't remember it. So, it would have been funny. All right. Let's talk about another example of axial chirality. So one of the things you'll see in organic chemistry that's used as a ligand, and I want to make sure I get this structure right. It's used as a ligand in some enantioselective reactions. Where are you? There it is. So this is kind of difficult to show. We're going to have to kind of show a benzene ring coming out of the page at us. And then we're going to have to kind of show this one going back into the page away from us. And then over here, we'll have it going back into the page away from us. And then at the bottom, it'll be sort of coming out towards us. I don't know if that makes any sense. Use your thumbs, and the way we've drawn it is kind of like this. This is the bond between those two benzene rings. And the presence of groups on either side restricts freedom of rotation. And because of that, you can actually separate the binol in enantiomers.
That's real fast.
Yeah.
The rings are still flat, right?
The rings are still flat, yeah.
Okay.
Yeah, so what this would look like you have to try to envision this by looking at it from the side, and maybe we'll build a model in Spartan and look at it. But basically, you would see, looking at it from the side, you would see the ring. This would be C1, 2, 3, 4, 5, and 6. So carbon 2 is here, carbon 6 is here, carbon 1 is in the middle. Carbon 2 is connected to a bunch of other stuff that links 2 and 6, right? And then carbon 2 also has an OH group on it. And then in the back, you've got And so I'm going to eliminate the connection between 2 and 6 because it's not going to be important for assigning chirality. Is that okay? In the back, you have, we'll call this 7 is in the middle, 8, 9, 10, 11, 12. So in the back, as we've drawn it, 8 would be sort of pointing down with an OH group here, and then 12 would be sort of here, right? Now, if you want to assign chirality, you simply say, okay, which group on the front, 2 or 6, has the highest priority? They're both carbons, so you look at what they're bonded to. Carbon 2 is bonded to an oxygen. That beats everything else that carbon 6 is bonded to. So 2's the priority here. 8's the priority there. Again, 2 to 8. That looks like a counterclockwise rotation, so we would call that M chirality. Now, I think if you've ever worked with or bought binol, I think they don't bother with the M or the P. I think they use R and S for it, but they must. I could be wrong. Does anybody know? Has anybody ever? Mario, have you ever worked with binol? No? Okay. We can look it up. Let's look it up. Binol. Yeah, see, they're calling it.
It's a ligand.
Yeah, you've used that as a ligand, and they're calling it R versus S. My guess is since R is clockwise, that would correspond to P chirality, and S is counterclockwise, that would correspond to M. Did I get that backwards? No. M chirality. So, yeah, it's, and they don't talk about assigning chirality anywhere there. So, P and M clearly hasn't caught on as much as R versus S, and so it's not necessarily universal. But being used to this idea that you can have chirality around an axis is an interesting one. Questions about that? Let's try to see if we can draw it in Spartan. My guess is that it's going to say, we don't know what in the heck that is. Oh, yes, but now I want to do this. Come on. Okay, let's try something. There we go. No. How do I do another benzene ring? I'm really wasting time. How do you like that hexagon? Okay. So this is essentially the view we had on the paper, right? Looking down the axis between the two bonds between benzene rings. And you can see how those OH groups are going to bang into each other and prevent free rotation at certain temperatures. Now, probably you could heat it up and get them to equilibrate. Molecule not in database. Sometimes, it'll show us, that's boring. It'll show us that it's less stable by a certain amount of kcals per mole to have the proton in another direction. Probably because of, A13 strain or something like that. Yeah, Dakota.
Even if the two OHs bang into and eclipse each other, it looks like you should be able to rotate the other direction to get the bonds to flip.
It looks like you should, except now these protons on the rings in the back are going to smash into each other. If you don't believe me, let's just make it space filling. Kind of stuck. All right. So this is used as a ligand for some enantioselective reactions, but the chirality comes from that axial chirality. There's no stereocenters in that molecule. It's just a stereogenic unit. What do you think, Adam? Have I got that? Is that? Why don't they call it M versus and P binol instead of R versus S?
Oh, just another thing to learn.
Okay. All right. Maybe because they don't, at Sigma Aldrich, they don't know what M and P are. They haven't taken this class. So maybe, should we, I know we need to start a letter writing campaign. All right. So we've talked about the R and the S, the E and the Z system, the P and the M system. I will point out that there's a D and an L system that involves Fischer projections. I don't care about Fischer projections, though I recognize they are useful in terms of seeing carbohydrate stereoisomers from each other. There's also something in your text about erythro and threo, which I really, really don't care about. But if you want to learn about it, you can. It's very rare that somebody will bust out erythro and threo. That's just...
Those people are terms.
Those people are what?
Are those people or terms?
Erythro.
They sound like old
Here's
people
my
on
son
the
erythro. Hey, that's names for future children. We call one erythro and one threo. Go ahead.
That may be more common in biochemistry because those come from the names of 4 carbon sugars.
That's right. Yep. So briefly, if you want to do a Fischer projection, and in the Fischer projection, the bonds that are up and down are going back into the page away from you. The bonds that are left and right are coming out of the page at you. So it's sort of like you're looking at the tetrahedron along one of its edges. And so you sort of have to remember that when interpreting it. It's not clear to me. I think you put a higher priority group up top and a lower priority group on the bottom. But this particular sugar is called D-erythrose, and its diastereomer is a 1-carbon epimer called... Why am I doing this? I said I didn't care about it, but then you guys asked a question. Threose. And so by analogy, people will use this as a way to distinguish diastereomers in unfamiliar contexts, or in contexts that are not the same. So here is this diamine where you can identify a group that looks like it should go at the top and a group that looks like it should go at the bottom. Frankly, I think you only use this if you're trying to sound smarter than other people. Which everybody loves a good heterocycle party trick. You know, if you can bust out some oxazoladinone name without blinking, it can be kind of impressive. But so this is the erythrodiastereomer, and this is the threodiastereomer. Yeah. It's sort of as useful, it's less useful than syn and anti. Syn and anti are only useful from a certain point of view, but erythro and threo are less useful because they're only significant by analogy. But potentially good names. Boy, and I suppose if we're going to stick with sort of gender-based endings to names in the tradition of various Latin-derived languages, if you had twin daughters, you could, and they were not identical, I guess you could erythra and threa or something like that. Okay. Is that an announcement? That's an inappropriate question. I'm sorry. Dr. Savage I think has a daughter named Esther, which he thought was appropriate for chemistry. He was not, however, able to convince his wife to name her Ethel Esther. But I remember one time when, she's all grown up now, but I remember one time when I took 351, 352 from Savage, he said that Yeah, if you ask her, she'll tell you that the reason she's named Esther is because she's the pretty est and the smart est and the...
Poor kid.
All right. Yeah.
And if we're sticking with the chemistry analogy, presumably she smells good.
Okay, yeah, Esther smelled good. I didn't ask about that. I figured that was too personal. Okay, so enantiomers cannot be distinguished except by other chiral molecules or other chiral environments. Your text talks about chiral crystallization or derivatization of a chiral molecule with another chiral molecule to enable enantiomeric separation. It talks about chiral HPLC and chiral shift reagents. A lot of that is not that hard to get used to if you are needing to do it. I know in the Michaelis lab they have a chiral HPLC column that they use to determine enantiomeric excess. You can also do it by plain polarized light. And for most chiral compounds that are newly synthesized, you have to report an optical rotation. So I just want to talk briefly about, let's see, what's the time? Yeah, I can't look at my computer because my computer says it's 9:41 in January. Talk briefly about how plain polarized light works and how it can distinguish between two enantiomers. So normally, what do we mean by plain polarized light? Well, light has two different components. This going to our right is the direction of propagation. That's the direction the wave is going. And because it's convenient to us, we're going to think about light as a wave instead of as a particle. As you know, light has two components. It has a component, an electric field component that is oscillating and is doing so orthogonal to a magnetic field component. So E is the electric field component, B is the magnetic field component, and we're just going to look at the oscillation of the electrical field as it propagates. And this is going to look just like a sine wave, except it would be actually like better drawn than that. But basically the wave decreases in intensity till you go through zero and then starts to increase in intensity in the opposite direction. Does that look sort of vaguely familiar? That's really all the physics we're going to get into. In light that's just out there, generated by lamps or the sun or whatnot, each individual photon is perhaps oscillating in a different direction. We will sometimes imagine with our Sith eyes looking down, pink Sith eyes, that would be awesome, looking down the direction of propagation and seeing the way that, so we're going to, this is like a Newman projection where the circle just represents that axis of propagation. And if over time we would see oscillation of the electric field up and down, right? Only in non-polarized light, if you superimpose many photons on each other, you're going to have oscillations in all possible directions. Whereas if you pass that light through a polarizing filter, you can weed out all of the photons that are not oscillating in the same direction. And that's called polarized light. Okay, with me so far? Now, okay, polarized light, that thing looks like it's planar, right? So how in the world is that distinguishing between chiral molecules? Well, here's where it gets a little complicated. In physics, you can think of things as being composed of, what's the term? Vectors in orthogonal directions, right? Like, anyway. you can think of plane polarized light as being the one-to-one sum of light that is polarized, but where the plane of polarization is actually rotating. I don't know what color we're going to use for that. I will just use red. That plane is actually rotating. In this case, it's rotating counterclockwise or to the left. And over here, it's rotating at the same rate, but towards, oops, the right. Okay? And at any given time point, if you were to add these two together,